Okay, so I'm going to talk to you about a project that's been recently funded by the National Science Foundation. And it's sort of particle physics based, which is my field. I'm an experimental particle physicist. So we definitely have big data, and we definitely need analytics to understand it, and we definitely have multi-scale modeling. So we sort of fit in here. We're a little behind on the statistical curve. And so what I'll do first is talk a little bit about the artificial intelligence and the likelihood pieces of this, and then I'll talk about the infrastructure. So this is a sort of better title. It's Cyberinfrastructure for Machine Learning and Likelihood-Free Inference in Particle Physics and Beyond. And so this is a collaboration between Notre Dame, NYU, and the University of Illinois. And so I'll just give a sort of brief, set the stage here. What we're talking about is particle physics is sort of the ultimate and reductionist investigation. So we're interested in the fundamental structure of the universe, the smallest constituents of matter, and we've sort of explored those things. Here are the sort of four forces of nature: the gravitational force, the strong force that holds nuclei together, electromagnetic force that's responsible for atoms, and the weak force, which is responsible for radioactive decay. And if you look at our periodic table, you end up with something like this: fundamental particles that we know and love, the quarks in red, the leptons in green, the gauge bosons in blue, and at the center of all of this, the Higgs boson, which is sort of works to give mass to all of the particles. And so I'm going to focus a little bit on Higgs physics because this is the most unexplored sector of the particle physics universe at this point, and it's where we actually have to work very hard to try to exploit the data as much as possible. So this is an interesting and sort of an inverse problem to many of the talks that we've been having here so far, in that the entire physics of the standard model is specified by this Lagrangian. I can just write it down. And this describes all of the physics that we know and love. So the initial state is highly specified. What's interesting then is this is a 19-parameter problem, 19 parameters to describe all of this. And so I can start out with an initial state and predict it completely precisely. Then I'm going to destroy it by running it through the rest of nature to the observation. And so we're going to end up trying to work back to this. And I'll explain how that works. So we have the standard model of particle physics. Why am I still talking about this? There are all sorts of signs of new physics out there. I'm not going to sort of read through the list here, but we know that there's dark matter in the universe. We think it's a particle-based thing, but we don't know how that fits in with our big picture. Certainly not in the standard model. There's dark energy. Neutrinos have mass. We have no idea where those masses come from. And there are various other things here that I won't go into any detail, but all of these things point to signs of physics beyond their standard model. Some of them are observationally very well established, yet we have no connection back to the physics that we can write down in the Lagrangian that I just showed you. So we have to extend that, and the question is, how do you extend that, and how do we tell how it has been extended by looking at our data? So we're trying to optimize searches for new physics in looking in these different directions, and so there are various ways we can do that, and so I'll describe that as I go through. So I work at the LHC, the Large Hadron Collider. Those of you who are familiar with this, there's a 27-kilometer ring buried about 100 meters underground underneath Geneva, Switzerland. There are 4 large experiments there. Here at HKU, they work on the ATLAS experiment. We at Notre Dame work on CMS. We're friendly competitors. And these are other 2 experiments that are sort of more specialized for doing different kinds of physics at the LHC. So these are giant machines. You can kind of, here's a person, I guess it's not a person, but here's a little cherry picker forklift. And here's the ATLAS detector. So these are giant things that generate huge amounts of data. And we're using these big things to explore the microscopic structure of the universe, which is the problem, actually. So what our typical inference goals are, this is what we're trying to do, is to look at this data. We're looking for searches, so we're either hypothesis testing or trying to classify events of one different type or another. We're measuring something, which means we're extracting an estimate of a parameter. Usually this is maximum likelihood based. Or trying to constrain parameters of a theory, how well can we observe the effects of underlying changes to that Lagrangian I showed you? And this gives confidence intervals as to how big those effects could be. So usually we're using likelihood-based techniques. And the problem is that as these become more and more complicated and as the dimensionality grows, we don't really have good statistical techniques for doing this likelihood-based inference when we have higher dimensions and everything gets smeared out and we're trying to reconstruct it from the final states of the data. So we sort of have this crazy bidirectional analysis structure where we have a parameter of interest that we're interested in measuring or constraining, and then we have a whole series of nuisance parameters, and my forward model involves many layers of latent variables, which I'll talk to you about in a second, but I have a probability here of observing X based on these things. And we have a very detailed way of simulating, starting at the very initial conditions all the way through to what this final data might look like. And then we have a gigantic quantity of observed data that we're trying to compare. And so the inverse problem becomes difficult because it's difficult to link the parameters of interest to the final state in the ways that we're used to doing it. So let me talk about the forward model here. So I have my standard model Lagrangian. If I'm interested in a particular state, I can draw a Feynman diagram. This is for WW fusion producing Higgs bosons with a particular decay mode. This involves about 10 particles. I can calculate this from first principles. So I know what my initial state is very precisely. Then, let me back up one here. So that's my first principle sort of drawing of what happens. That I can calculate. Next, I have to see what this final state is going to look like in my detector. So first I have to allow these particles to begin to interact with the universe. In this case of quarks and things like that, this means that they interact via the strong force, which ends up with all this sort of extra radiation in here, this sort of decorating these particles into observable things. So this is we sort of know what the first principles are here, but we can't calculate this precisely. So, because everything is non-perturbative, so we use simulation to do this. So, but it's based on physics. Then we have a phenomenological model that produces the particles that we actually see. And so you can see I'm just layering sets of latent variables on top of this. So now we have something like 100 particles in the final state. That's my sort of microscopic initial thing. And so then I have to observe this. So I have this detector. So the initial thing that I just showed you is all happens within 10 to the minus 16 meters. And now I have something that's 10 meters wide that I'm going to observe this with. And I'm going to try to figure out what happened to the original little red things down here based on the information that I'm recording from something like 10 to the 8th sensors. All of this has to be simulated. So in order to do this, we have detailed engineering drawings, first principle descriptions of particles' interactions with matter. We propagate these things through and integrate the microstructure of all of these interactions. So this is how we generate basically simulated electronic signals in this detector that are caused by microscopic subatomic particles. So once we have that, I have my simulated event here with all these different particles swirling around in it. I have another layer of things that I have to apply reconstruction algorithms to define what I mean by observing a particle. I have to connect the dots here to say, well, was there an electron or a muon or something over here? And those objects, these are the sort of representation of the underlying physics of that initial state as observed by the detector. So it's yet another layer of processing. And so I end up with, finally, an observed set of variables x. Okay, so that is the issue. And so what I'm trying to do is then relate this back to where we started. Here's a picture, actually, of what that actually, this is a Higgs boson decay candidate in the Atlas detector. And so you can see these red lines here are 4 muons that come out from this detector that are a signature of a Higgs decay. And then I have all this other junk in here that I'm somehow processing. I have to figure out how to distinguish interesting stuff from junk. And so you can tell that this is a very, very complicated system. I'm reducing it to sort of 10 parameters that describe the objects of interest. And then, in fact, I'm going to do it even worse. So I start out with 10 to the 8th sensors, tens of parameters, and then I'm going to have one real value quantity after all of this that's, say, the particle mass of the Higgs. And so I'm going to put that in a univariate histogram here. And so if I'm going to discover the Higgs, I'm going to find a peak in the invariant mass of my 2 muons. And if that is not consistent with the background, that's my discovery. So this is relatively straightforward, and we've gotten really far by doing analyses like this. If I can find a mass peak, I'm a really happy person. But this is not going to get us through the next level of physics at the LHC. So as we start to look for more subtle effects in higher dimensions, then this sort of modeling and choosing good variables with skilled insight and approximating these likelihoods by histograms, we don't have enough simulation horsepower or data to actually do this and populate everything in more than one dimension. So this is what I'm trying to address here in this talk. And I just said that. So if we start adding things to those Lagrangians, what we see is that there are potential for correlated effects in many different variables across the spectrum. So not only do I not have one variable anymore, I have correlations between them that will be signatures of new physics. The likelihood is completely intractable. I can't write down a closed form for it because I have different layers of simulation or masking of these effects. And so one of the things that's gone on is for people who have started to develop I guess there's this standard class called likelihood-free inference. And so we're trying to use the information just from the forward model in ways that are compatible with these higher dimensional analyses. So now this, to many of you, may look really simple. And so I'm hoping that you can say, oh yeah, you should do this. So that's where I'm going with this. So we need methods that are compatible with higher dimensional analyses. People have looked at approximate Bayesian computation. It doesn't scale well, so we have a curse of dimensionality there. And so people have been looking at probabilistic programming systems and neural density estimation, so some techniques that can allow us to explore this space and come up with representations of this forward model that allow us to infer what we're actually seeing in the initial state. So just to toss out one of these that was developed by one of the collaborators on this, which is Kyle Cranmer and friends. So one of the things that we have, because we have this knowledge, complete and precise knowledge of the initial state, we have this calculable relationship between the variable of interest and sort of the first layer of variables. That we can calculate exactly. Then we smear it out by successive introduction of other latent variables here. But these things basically don't depend on the initial state, and so they in principle should factorize. So if I'm interested in an optimal statistical test, I can look at the likelihood ratio comparing some set of parameters theta 0 to some other set of parameters theta 1. This is optimal in terms of deciding between them, but this depends on all the other mess of detector simulations and whatnot will cancel out, but I'm still left with a ratio here that depends on the latent variables. However, I also have information in terms of how this state evolves. So I can also look at the gradient of this, or the score, and so I can use this to augment my calculations of how to connect these pieces up back to the final state that we're actually interested in. So one of the things that you can do is you can look at the L-squared loss function for a function g that only depends on x, but we're trying to approximate g and its dependence back on these latent variables. And so this is just sort of a definition of it. The solution that minimizes this, it looks like this form here. And so if I take g of x of z and put in instead the likelihood ratio that I'm actually really interested in, then I get this form of here. And this, as you do this out, integrates out the z dependence. And so I have g, the minimized function, the function that minimizes this loss function is actually the likelihood ratio without the latent variables. So if I use this loss function of this form, I can regress to the true loss function. And I can get rid of my dependence on all this intermediate stuff. And so I can also produce a true score at the same time. So this is an interesting way of pulling out and using the information inside of the simulation. So symbolically, this kind of looks like this. I have my simulation. I can extract these forms. one of the things that was noticed is that computing this regression is a great opportunity to induct machine learning into this, because I can use that to figure out the optimal function and make it be rapidly computable. And so that's a really nice feature of these models. And then once I have my approximate likelihood ratio, I can do physics and relate the original parameters of interest, or at least constrain them based on the observed variables that I see. So the training data is, of course, derived from simulations, which is where the next portion of the talk comes from. And there are various methods that people are looking at for optimal sampling of the variables as we go forward. So here's some various regression methods that were tested in terms of how you actually approximate this optimal likelihood ratio. And so there's sort of clever acronyms that people have come up with. One of the interesting things that you can do is which I won't have time to go into detail here, but you can actually, by expanding around the fixed point, if you're not traveling very far away from the parameter set, the sort of standard model parameter set, if you're looking at small deviations around that, then you can have local sampling, which dramatically reduces the need for large sample size. So these red and blue ones are actually approximations in the local space around the sort of fixed point that we know where we're living, if we're looking for small perturbations around that. So that's a dramatic change in terms of the resources that are needed. So just to show one example here, if you use some of these optimal methods and compare your ability to constrain additions to this Lagrangian, adding some new physics, you end up with something that looks like this. Or our standard 2D histogram approach would be these orange dots, where the truth is basically sitting here at 0, 0. And these are our confidence level contours here. And you can see that both of these methods have tighter constraints on the 0, 0 point than this sort of what you would get from a 2D histogram being really stupid way of plotting it. But that's basically our standard thing to do. So this is an improvement of about 16% in sensitivity, which if you fold that back into sample size, it means almost a factor of 2 more data you would have to collect to get this improvement if you didn't use these statistical methods. So this is a promising way of looking at the data. So let me switch now to talking about sample size, because if you want to use these methods, you actually do need large sets of Monte Carlo to be able to train the neural nets and to perform these tests. So let me switch from the AI and likelihood-free inference part of this to the scalable cyberinfrastructure part. And so let me just throw a few facts down here. So at the LHC, we have 40 megahertz collision rate, which means that at 1 megabyte per collision, we regenerate 40 terabytes per second. Now, we also throw a huge fraction of that away because it's not necessarily the most interesting data to look at, and we've already studied it for the past 50 years. So it's selectively but very carefully thrown away. So we only write tape at a kilohertz, so there's a very large data reduction here. But even so, we still generate data sets of 20 petabytes a year or so. So this is not a small data. The interesting processes that we're looking at are relatively rare. Every billion collisions produces a Higgs boson. So not only is this a big data problem, but it's a rare signal inside of big data problem. And of course, we want to collect lots of Higgs bosons and study them. So everything that we're looking at in terms of backgrounds or other processes that can mimic Higgs boson signals are in tails of distributions. So simulating something that looks like 40 megahertz is not practical. It's just a gigantic fraction of data. And so there are all sorts of techniques that I don't have time to talk about of how one can use to estimate the backgrounds that sit underneath this 1 in a billion, because there are lots of them. So then switching to the computing side, if I'm going to simulate collisions, even simulating one of them could take minutes. So I cannot certainly simulate billions. Well, I can simulate billions, but I can't simulate hundreds of billions. But if I'm doing a parameter scan, I have to do a grid, and I have enough points at each enough events at each grid point to do machine learning training. So this doesn't scale well either. And so what we're interested in doing is to build some new cyber infrastructure that will help with this. And so one of the things that we're going to do is to extend this platform called Rhianna, which was developed with its CERN, with a DASPOS project, which is something that I was leading for the past few years, which was focused on knowledge preservation in analysis, and also developed with this recast project, which developed some of the internal tools of this. And so basically, this is a way, it's a system that supports the complete capture of an analysis workflow in terms of chaining together all the different computational steps. You have your input data, you can completely specify input and output for each analysis step, and it is set up so that it runs, right now it runs at CERN on their OpenStack cluster. And so you can log into this thing. If you've preserved your analysis, you can press the button, it will go through and rerun all of your analysis for you to the point of even making plots at the end. And so this is something that's being set up at CERN at the moment, sort of in beta. It's built of sort of standard components. We have at the moment the Kubernetes orchestrating containers on this back end. So it's something that could be stood up anywhere. In fact, we have a version of it running at Notre Dame right now because we're testing the new pieces that we're building. So it's all based on Docker containers. But that's not necessarily the final word in that. But in any case, this exists, and our proposal is going to extend it. And let me just show you what these workflows look like. So this is an actual specification of a workflow. And each box in here is a container that gets executed. And so this is a particle physics analysis workflow that is set up inside of this system. This is written in the Yachtage workflow language. We've also started working with a common workflow language, which is more used in biocomplexity and biology systems. But this is sort of similar. These are the same workflows in these two different languages. So these will allow you to do a complete chain of this analysis. And the nice thing about this is that, I mean, you can see that these are hideously complex things, but you can write them down and they'll execute. So this is really nice for machine learning training, where you generate data sets and you can pick them apart and send them off to different training nodes or whatever. And so this is a nice way to look at machine learning training at scale. And so what we're going to do then is to take this Rhianna system and add new components to it. So one of the things we'll do is to add some new workflow languages. There's Parcel, which is partially developed at UIUC, which is sort of a functional programming kind of language. There's Nextflow, which has been used on various HPC sites. And the idea to take this to scale is to add a back end to the job execution controller that will allow this system to interface with the standard HPC schedulers and deploy containers on HPC systems. So we will be able to run this on any of the large NSF HPC systems and then automatically do machine learning training at scale with the complexity that I showed you. And then in order to do that, of course, we have to containerize the algorithms so that they'll run on these nodes. So this is a kind of, so we're starting with the central system and then adding capabilities to the outside. But we're expecting to be able to deploy this within the next sort of year or so on these big systems. So I've only shown you a tiny slice of the sort of machine learning and AI work that's going on in particle physics. Other things that you could read about if you're interested. Again, machine learning, everyone is excited about it. I think we're throwing every possible letter of neural net. I think we're going to run out of letters here in terms of the different neural nets that people are trying to invent. Trying to do this, so GANs are hot for simulation approximations to try to reduce that minutes of computation to seconds for generating events. People are looking at event reconstruction, analysis, classification. Pick your favorite thing. I think people are distracted by many shiny new objects personally, but some of these are actually increasing performance and some of them are not doing so well. There are also AI models being developed for the computational systems themselves in terms of spotting sites that are not doing so well and suggesting corrective actions. We have several hundred petabytes of disk worldwide that have to constantly be monitored for popularity of data sets because we don't have enough disks to store them all. So we have systems that are looking at these and trying to decide which data should be placed where so that the analysis can be optimized. Within this project that I just talked about, there's some other things that we're doing. We have a matrix element computation, machine learning for that. So basically, this is a very computationally intensive technique that exactly computes those original particle physics variables for each event. If you could teach an AI to learn what the answer was, then you don't have to do this, or you only need to do it once, and then you can actually compute very fast with that. There's a bunch of work going on in terms of uncertainty quantification, because all of these things have systematic errors associated with them. Can you incorporate that into the machine learning training? And so there's some work there. And then I talked before about optimization of the simulation-based workflows. Can you, I mean, this is an old problem, but it still comes up. Do you have to generate all the Monte Carlo? Can you selectively use the phase space of what you're looking at to optimize your simulation? Again, these are not new problems, but they're sort of new to particle physics just because we're trying to confront a giant increase in data and a giant broadening of this dimensionality of the systems. So, so just to conclude then, most of what we're doing are based on known priors. So this simplifies, but as I said, we're trying to measure processes at maybe 10 to the minus 18 meters based on detector elements that are 10 meters away. So it's definitely multi-scale obfuscation, and this is something that we need to deal with. And we've come pretty far with just making histograms and looking for bumps, but this is not really going to be the future. So we need new computational and statistical methods to look at these higher dimensional problems. The signals are more subtle, and the data sets are just getting larger, and computation isn't getting cheaper that much. So this project that I've described is a small piece of the work, but I'm hoping that we can have more collaborations in this vein. So thank you.
So Mike, in the beginning you saw this Lagrangian with many parameters. So I will assume you know some of the physics because there was a structure of Lagrangian and there were lots of parameters
Sure.
that you don't know. So because I'm thinking of something else that is irrelevant now, but I'm wondering, is there any attempt to actually specify the Lagrangian implicitly as a neural network and just go and learn it from indirect data that you observe, so that way maybe you can have the hope of discovering physics, that your equations, the form, you know, in the Lagrangian you had some field variables, some gradients.
Yeah.
So you assume things, but maybe there's something else that.
Well, I think that so the Lagrangian I showed you is basically very well established from particle physics experiments over the decades. So this thing, this is the electroweak symmetry breaking. This is the coupling of the weak force to the. So these are things that we actually know. What we do in the new physics part is we add new terms that haven't been excluded and look for subtle effects based on the structure of those new terms. So maybe I should have explained that a little more. And so we're looking for new physics by just plus some other stuff that may have a small coefficient, but has a field structure that doesn't violate all the observations that we have already. So we could, in fact, do something like that, what you just suggested, because we don't know what the form of the new terms are. We can guess, but if we start to observe new physics, we will have to do something like what you said. We have various sets of new terms of models to test. We'll have to figure out how those are actually appearing in nature. So what we're doing at the moment is sort of the inverse. We're sort of positing what the new terms could look like, and then trying to explore all different combinations of those, which it's hard to do that. Yeah.
I can steal that. So this is a great talk. I'm just curious, how do you move petabytes of data from the source into a distributed computing environment?
By building your own 100 gigabit network that no one else can use.
Guess that works.
I mean, seriously, there's a high energy physics LHC worldwide network it's parallel to a lot of the other ones, but we have dedicated cables that go across the Atlantic, for example.
Does that move data into like the NSF
So no, there's something called the Worldwide LHC Computing Grid, WLCG, which is actually funded by high energy physics and national governments. And so it's not part of the NSF computing infrastructure. It is funded by the NSF, but these are machines that, I mean, it's sort of Purdue, for example, has a big computing center, part of which has nodes that are dedicated to particle physics. So what usually happens is you have a big data center that has a bunch of nodes, and you know, some fraction of them at some point of time are used for particle physics, and you know, when they're not used, they're shared back and forth. But that has been the model. So there's been a lot of investment in dedicated hardware. And I guess we're very fortunate that's been the case for, you know, the last 15 years or something. Thank you.